This is Geometry, Section 2.3, Biconditional Statements. So, to review, first, a postulate is something, we've talked about postulates before, postulate is something so obvious we accept it to be true. Okay? So we had two major postulates that we've talked about before. The first was the segment addition postulate, which basically said if I've got a segment like this, A, B, C, then the segment addition postulate says the distance between A and B plus the distance between B and C equals the distance all the way from A to C. Angle addition postulate was similar, so if I've got an angle that looks like this, and say this is D, E, F, G, then angle D, E, G plus angle G, E, F would equal the whole angle D, E, F. The two parts equal the whole. Same thing for segment addition postulate and angle addition postulate. Just add the pieces together, the pieces equal the whole. So postulates are something that we can write as what is called a biconditional. So what is that? To save time and writing, so the last section was a lot of writing, to save time and writing we can combine a conditional, which is an if-then statement, a conditional and its converse into just one sentence. So for example, if we have the conditional statement, if it's July 4th, then it's Independence Day. That's a true statement. The converse would be if it is Independence Day, let's abbreviate, then it is July 4th. Assuming that we are in America, that would also be a true statement. The combination of the two, we're going to write it as it is July 4th if and only if it is Independence Day. And that would also be a true statement, again, assuming that we're in America. So, although it's an odd way to write a sentence, we're always going to write the combination of the original statement, the conditional statement, and the converse as A, if and only if B. So, a biconditional, we take the hypothesis, then we write the words if and only if, an abbreviation, so there's even more abbreviating, an abbreviation for the words if and only if is capital IFF. So IFF, all capital letters, means if and only if. So the hypothesis, if and only if, the conclusion. So whenever a conditional and its converse are both true, then the biconditional is also true. If either the conditional or the converse is false, so they do not both have to be false, but if either one is false, then the biconditional is automatically false. So, for example, if we have this biconditional right here, today is Sunday, if and only if today is Easter. Original statement would be if today is Sunday, then today is Easter. So, if we look at that statement, if today is Sunday, then today is Easter. Is that a true statement? Well, no, because there's a lot of Sundays that are not Easter. The converse would be if today is Easter, then today is Sunday. That would be a true statement because Easter always falls on a Sunday. So if today is Easter, then today is Sunday. Since this original statement, since the conditional was false, the biconditional is automatically false. If we look at that statement, today is Sunday, if and only if today is Easter, well, that doesn't make sense because not every Sunday is Easter. So that statement is false. Another one, the biconditional is a shape is a square if and only if the shape has four sides. So the conditional would be if a shape is a square, then it has four sides. That would be a true statement because all squares have 4 sides. Converse would be if a shape has 4 sides, then it is a square. That would not be a true statement. That would be false because we could have a shape that looks like this. This has 4 sides, but this is not a square. So, since this statement is false, biconditional is automatically false. Conditional. If today is December 25th, then today is Christmas. That is a true statement. Converse would be if today is Christmas, then today is December 25th. That is also a true statement. If today is Christmas, then it's December 25th. Biconditional statement, so if we combine the two, you never start a biconditional with the word if. You always put the if in the middle. So, biconditional would be today is December 25th if and only if today is Christmas. Since both of these statements were true, the biconditional would also be true. This one gives us the converse. If a number ends in 4, then the number is even. Well, to write the conditional, we just switch it back from what it turned into. So, if a number is even, then the number ends in 4. So if a number is even, then the number ends in 4. Well, that is not true. That's false because there are many even numbers that don't end in 4. The converse, the statement we were given, if a number ends in 4, then the number is even. That's a true statement because if it does end in 4, then it has to be even. But this statement is not true both ways. So if we write the biconditional, a number ends in 4 if and only if it is even. Since this part was false, this part has to be false. The biconditional has to be false. Notice how I wrote this part, the hypothesis of the converse, first in this one, and I wrote it second in this one. So today is Christmas, today is Christmas. I wrote it second for this one, and I wrote it first for this one. For the biconditional, it doesn't matter which order you write it in, as long as you split up both pieces and write this piece if and only if in the middle. Next one, the biconditional is segment AB is congruent to segment XY if and only if the distance between A and B equals the distance between X and Y. Well, that's a true statement if I just look at it, because two segments are congruent if their lengths or their distances are the same. So that would be a true statement. The conditional would be if segment AB is congruent to segment XY, then AB equals XY. That's a true statement, and it's also true the other way. The converse, if AB equals XY, then segment AB is congruent to segment XY. All three of those are true. Last one, if 3 points form a triangle, then the 3 points lie in a plane. That is true. Any 3 points make a plane. The converse would be if 3 points lie in a plane, then they form a triangle. That is not true, because if I have 3 points that are collinear with each other, that form a straight line, those 3 points would obviously not form a triangle. So if 3 points lie in a plane, then they form a triangle. That's false, because 3 points could lie in a plane but lie on one straight line and not form a triangle. So the biconditional would be 3 points form a triangle if and only if, I'm going to use that abbreviation that I told you about, capital IFF, if and only if they lie in a plane. Since the converse was false, the biconditional is also false. Last thing, a definition. So definitions, and like I said at the beginning, postulates. So definitions and postulates can always be written as a biconditional. So, an example, definition of a triangle? Well, a triangle is a shape with 3 sides. Simple definition of a triangle. So we can write that as a biconditional. We can write a shape is a triangle if and only if it has 3 sides. Or like I said, you could also write it the other way. A shape has 3 sides if and only if it is a triangle.